Now let us move on to chapter 6. Application of derivatives. Increasing and decreasing function. Let I be an open interval in the domain of f. Then f is increasing on I if x1 less than x2 in I implies f of x1 less than or equal to f of x2. And strictly increasing if x1 less than x2 implies f of x1 less than f of x2. Increasing function means as the value of x increases, f of x also increases. Here x1 less than x2. So f of x1, value of the function f at x equal to x1 is less than or equal to f of x2. F of x2 is the value of f at x equal to x2. So when x1 is less than x2, f of x1 is less than f of x2. If it is equal, only increasing and strictly increasing, small difference. Strictly increasing means when x1 less than x2, f of x1 should be less than f of x2. Here in this case, increasing, that means when x1 is less than x2, f of x1 may be equal, less than or equal to f of x2. So here strictly, that means x1 less than x2 implies f of x1 should be less than f of x2. Here it can be equal also, f of x1 less than or equal to f of x2. F of x1 can be equal in the case of increasing. But strictly increasing means x1 less than x2 implies f of x1 less than f of x2. So in the case of increasing function, as the value of x increases, f of x also increases. Now decreasing function. Decreasing on I if x1 less than x2 implies f of x1 greater than f of x2, greater than or equal to. That means when as x increases, f of x decreases. X increases, f of x decreases. So as strictly means x1 less than x2 implies f of x1 greater than f of x2. Here when x1 is less than x2, f of x1 is greater than f of x2. That means as the value of x increases, f of x decreases. Opposite direction. So decreasing means it can be equal also. F of x1 greater than or equal to f of x2. But in the case of strictly decreasing, x1 less than x2 implies f of x1 should be greater than f of x2 strictly. So that is increasing and decreasing functions. Generally, increasing function means as the value of x increases, f of x also increases. Strictly means as x1 less than x2 implies f of x1 less than f of x2. Strictly decreasing means x1 less than x2 implies f of x1 greater than. Here less than, here greater than. F of x1 greater than f of x2, opposite direction. As x increases, f of x decreases. That is the increasing and decreasing functions. Then theorem related to that, let f be continuous on closed interval AB and differentiable in open interval AB. Then f is increasing function in the closed interval AB if f dash x means derivative of f of x is greater than 0 for every x belongs to open interval AB. And f is decreasing in the interval, closed interval AB if f dash x derivative is less than 0 for every x belongs to open interval AB. And f is a constant function in interval AB, closed interval AB, if f dash x is equal to 0. So depending upon, so theorem we have to study only the statement, proof no need to study. So understand that when the derivative of the function is greater than 0, then the function is increasing function. And derivative is less than 0, then function is decreasing. In some cases, derivative is equal to 0. In that case, the function is a constant function. So this is a very important theorem. So to check whether the function is increasing or decreasing, we are using the theorem. So we have to find out derivative f dash x is greater than 0 or less than 0. If the derivative at that point is greater than 0, function will be increasing. And if the derivative is less than 0, then function is decreasing. And if the derivative is equal to 0, then that means the function is a constant function. Function is a constant function. So that is a very important theorem. So understand what is increasing function and decreasing function, strictly increasing, strictly decreasing, and theorem. Theorem. Now exercise 6.2, first question. We have to prove that f of x equal to 3x plus 17 we have to prove that this function is strictly increasing in the set of real numbers. We have to prove that this function is strictly increasing in the set of real numbers. We know this function is polynomial function and domain is set of all real numbers. So we have to prove that this function is strictly increasing in the set of real numbers or in the domain. So here we are using the theorem. Using the theorem, if f dash x is greater than 0, we can say the function is increasing. So here we have to prove that this function is strictly increasing for every x belongs to R, set of real numbers. So for that we are using the theorem and we find f dash x, derivative of f of x. F of x is equal to 3x plus 17. Therefore f dash x is equal to here 3 into derivative of x, that is 1. That is 3 into 1 plus derivative of 17, 0. So derivative f dash x is equal to 3. It is a constant. So this f dash x, we know that the derivative which is 3. 3 is always greater than 0. So 3 is a number which is greater than 0. So if f dash x greater than 0, we can say that the function for every x belongs to R, for all real numbers, x be any real number, f dash x is 3, that is greater than 0. So for every x belongs to R, f dash x is greater than 0. Therefore we can say that f of x is strictly increasing. See, some cases, suppose we are getting f dash x greater than or equal to 0. So in that case we cannot say that strictly increasing, only we can say increasing. So here, since f dash x is greater than 0, we can say that f of x, therefore f of x is strictly increasing. Strictly increasing for every x belongs to R. So this function f dash x is greater than 0. Therefore f of x is strictly increasing for every x belongs to R. Or we can say f of x is strictly increasing in the domain of the function or for all real numbers. So that is the question number 1. Then question number 2. F of x equal to e raised to 2x. F of x equal to e raised to 2x. Here also we have to prove that the function is strictly increasing for every real numbers, for every x belongs to R. Here also we will find the derivative, first derivative, f dash x. So find f dash x. So here f dash x equal to a derivative of e raised to 2x. What's the derivative of e raised to x? E raised to x. So what's the derivative of e raised to 2x? E raised to 2x into derivative of 2x. That is 2. So into 2. So f dash x equal to 2 into e raised to 2x. And this is the derivative and we have to prove that this is greater than 0 for every x belongs to R. So we know, see, this is one special function, exponential function, e raised to x. Remember that e raised to x is greater than 0 for any value of x. See, suppose when x is negative number, then also e raised to x will be positive. For example, suppose x equal to negative 1. Then e raised to x, that means e raised to negative 1. What is e raised to negative 1? That is same as 1 by e, which is a positive number. So even if x is negative, e raised to x will be positive. So remember that function, it's very important. So e raised to 2x, whatever be the value of x, whatever be the real, if x takes any real number, e raised to 2x will be greater than 0. It will never be equal to 0. So this 2 into e raised to 2x is greater than 0. This is greater than 0 for every x belongs to R. This is greater than 0 for every x belongs to R. So since it is greater than 0 for every x belongs to R, for every real number x, x can be any real number, positive or negative or 0, e raised to 0, e raised to 2 into 0, e raised to 0 means 1, which is also greater than 0. So whatever be the value of x, this f dash x derivative is greater than 0 for every x belongs to R. Therefore, we can say f of x is strictly increasing. F of x is strictly increasing for every x belongs to R. So for every real numbers, this function is strictly increasing. If it is greater than or equal to 0, in some cases, if it is equal to 0, we cannot write strictly increasing. Then we can write only increasing. Here it is greater than 0 for every x belongs to R. Therefore, we can say f of x is strictly increasing in the domain or for every x belongs to R. Okay.